Well, this lab is about diodes and about what nice things diodes can do for all of us that you use actually every day. So we've talked about resistors. We did a Wheatstone bridge lab measuring resistors in series and parallel and so forth. We talked about capacitors. We did a capacitance lab measuring the time constant of a charging or discharging capacitor. And of course, we've talked about current, which is the flow of electrons, we'll say Ben Franklin's positive charge is okay, through a circuit. And we did Kirchhoff's rules experiment to find out how we can employ all these things to figure out the current in a rather complicated circuit. So that's where we've been. Where we're going now is talking about a diode. And here is the circuit symbol for a diode. And it looks like there's an arrow there. It's a triangle, but okay, let's translate it as an arrow, because what a diode does, this is the negative end of the diode, and this is the positive end of the diode. And your diodes are in a little tube here, and the banded end of that tube is the negative end, and the unbanded end is the positive end. So you can take a look at that little black cylinder, and there's a silver circle on one side. That's the negative end, represented by that bar there. So the neat thing about diodes is current flows this way, but it can't flow that way through this diode. It's a one-way, sort of like a check valve in a plumbing system or a system like that. So it's an electronic check valve. Current can go this way, but it can't go that way. What that means is, well, if you take a look at the inside of a diode, and we won't get too much into this, if this is the sort of the inner part of this diode, there is a what's called a P material and an N material. P means positive, N means negative. This P material has materials that would like to have some electrons, and the N material is made up of materials that would like to give off electrons, such as, like in the periodic table, the fifth column of the periodic table, or a valence of 5, and the valence of 3. So the valence of 5 likes to get rid of electrons, and the valence of 3 materials like to accept electrons. In fact, they're called donors and acceptors. Anyhow, that's way too much. It takes about 2 days in our condensed matter class, senior level class, to explain really how does this diode work. Right now, we're just saying, here's a diode. What can we do with it? What good is it? It's a one-way resistor, so why do we need that? All right, so here's the first circuit. We're going to get to this this concept in a bit. This thing here is called a transformer, and it uses changing magnetic fields to produce voltages. That's Faraday's law, Lenz's law. You'll be getting to that. It's a very important law. It's kind of a abstract law, but it's the law that helps us transmit power all around the world and have all the electronic devices that we have. So it's a pretty important law. So anyway, this is the primary and this is the secondary. And there are two types of transformers. There's a step-up transformer in which this voltage here is going to be higher than this voltage here. And there's a step-down transformer in which this voltage here is going to be smaller than this voltage here. So actually, on your experimenters, you have in the center section of the faceplate a 3-terminal connector that can connect to 117 volts AC. And this is labeled as 15 volts AC. And this transformer, the secondary transformer, has what's called a center tap on it, which we will use, and that's the ground. So that's the 0-volt connection. So what we put in here from the wall is a signal, a sine wave that looks like this. Actually, that has a peak-to-peak value of about 340 volts. And yet it's called 117 volts AC. The reason for that we'll get into more, what we've already gotten into in terms of using the oscilloscope. 117 is 340 divided by 2 times the square root of 2. This is the peak-to-peak voltage, and this is what's called the RMS, root mean square, or the equivalent DC voltage. And we'll see more about that in a little bit. So here's a transformer in the middle of your experimenter. It has a center tap, and so it has 2 outputs. This is pin 1, this is pin 2, this is pin 3. So let's hook up, and this is 15 volts AC. So let's take this transformer lead from pin 1 and hook up a little circuit. We're going to have a resistor and then a diode. This is pin 2. So this is simply the connection to one side of your step-down transformer and the ground. This is ground, or 0 volts. Okay, well, we just talked about what how a diode works. That is, diodes will let current go this way, but they won't let it go this way. That's their job. They're a check valve, one-way street for electrons or Ben Franklin current flow. So current can only flow this way. So if we look at what we're putting in here, which is a sine wave like this we just talked about, this is a 15 volt peak-to-peak sine wave, not a 117 volt peak-to-peak sine wave. And if we put our oscilloscope here, this oscilloscope, channel number 2, channel number 1, we can see that this is a 15 volt RMS, about a 45 volt peak-to-peak input voltage. Okay, so what goes in? Something that looks like this, which is about 45 volts peak-to-peak. But the diode does not let current flow that way. It can flow this way, but not that way. It can flow this way, but not that way. So what you see in your oscilloscope channel 2 is this, sine waves with the bottom halves thrown away. Now, this is actually DC voltage. The careful definition of DC voltage is a voltage that sends current only one way. It doesn't send current one way all the time, in this case, and it sends current one way in these little spurts, these little bumps, these little sine bumps. So this is still DC voltage because current can only go that way thanks to this diode. So this is what we see on channel 2. And if you measure very carefully, which I'd like you to try to do, so you want to first measure this value here. What is the peak-to-peak value of the input voltage? Then you want to measure, there's no peak down here, you want to measure the peak value of that voltage. Let's say this is 45 volts. So half of that is 22.5 volts. If you measure this very carefully on the oscilloscope, again, your oscilloscope has a grid which is in centimeters, and it has a 10 centimeter grid this way and an 8 centimeter grid this way. So theoretically, if you set your vertical gain control to 5 volts per centimeter, you should be able to measure 8 times 5, or 40 volts peak to peak. Unfortunately, you have 45 volts peak to peak. So the little, as you already know, the little trick we have to do is we put it out on the center line, we put the ground on the line below it so we can measure the top half, and we put the ground on the line above the center line so we can measure the bottom half, and we add those two together, and you'll get again about 45 volts. This is not going to be the same transformer as you used earlier to measure this in your experiment, but it'll be about the same voltage, 45, 46, 47 volts, somewhere around in that range. So we have to use the maximum, least sensitive scale because these are pretty big voltages. So if this is 22.5 volts coming in, I'm just making up these numbers, you're going to see this is going to be more like 22.0 volts coming out. You have to measure that very carefully. So if you have a peak like this and you have a grid, this is 0, 5, 10, 15, 20, and so forth. You measure this very carefully. And again, if your oscilloscope is not calibrated, you have to calibrate it. If you're looking at channel 2, you might want to check the calibration on channel 2 to make sure that if it's 4 centimeters high, that's 4 times exactly 5, which is 20 volts. Or maybe it's not calibrated properly, and you have to multiply by a fudge factor like 0.98 or 1.02 to make the voltage correct. But in any case, you can read this to probably the nearest millimeter on the screen. That's the distance halfway between two of the small marks on the vertical and horizontal scales. So please measure that carefully and see that this voltage is a little bit less than this voltage, something like a half a volt less. And the half a volt there comes from what's called the junction potential here. And the first thing you're going to measure with these diodes, with just a regular multimeter, which has a special setting on it to determine the junction potential of the diode. If the junction potential is about 0.6 volts, then it's a silicon diode, and if the junction is about 0.3 volts, it's a germanium diode. So you need to figure out what kind of a diode are we working with here. And so if it's a silicon diode, this is going to be about 0.3 volts lower than this. And so check it out. If it's a germanium diode, it's going to be about 0.6 volts less. So measure that carefully. See if you can sort of corroborate that in your measurement that it is silicon or germanium diode as your voltmeter told you in the first place. Okay, that's our half wave. It's called half wave rectifier because it throws away half the wave. It's not very efficient because it throws away half the wave. All right, so let me draw the more complicated circuit from figure 2. So we have a transformer. We won't draw it all here, and a center tap. And we have a diode up here, and we have a diode down here. And we know all about diodes there. But this is the ground, and this diode is going to go through a resistor to ground. Run another wire from this diode. This is the circuit you've got to hook up. This little thing here indicates that this wire is not connected to this wire. It's looped over it and connected up here. So you can, on a PC board, you can do that. You can connect this diode to this diode in the same column on your PC board. Okay, so if you look at oscilloscope 1 input, you see what you saw before for the first part of the lab, about a 45 volt peak to peak or 22 volt roughly 0 to peak value. If you put your oscilloscope here, oscilloscope channel 2 here, you can measure what's going on in this resistor. Now, this is a really interesting circuit because you know that these diodes, so this is the ground, this is the positive side, we'll call that the negative side of this transformer. So when the transformer is on this part of the input, this is positive, and when it's on the lower half, it's negative, and this is positive. In other words, these switch around. Positive, negative, and then they become negative, positive. So during this half of the sine wave cycle, this is positive, and so this diode is going to let current through here. And the current goes through the diode, and it goes through the resistor, and then back to ground and around and around and around. Okay, so that's for this part of the cycle. We'll call this part 1 and part 2, diode 1 and diode 2. In the second half of this sine cycle, this diode conducts, and this diode doesn't because it's hooked in backwards now all of a sudden. And so in the second part of this circuit, we have current going through this diode, and you notice it goes through the resistor in the same direction. So we have a voltage drop across the resistor that has the same polarity, whichever diode is conducting. First this one, then this one, then this one, and this one. And so you know what's going to happen. We're going to get an output that looks like this. This is diode 1, this is diode 2, this is diode 1, this is diode 2, and so forth. And so this is called a full wave rectification, which means it takes the full wave and electronically flips the bottom half over and puts it up on top because of the way these diodes either conduct or block the current going backwards through them. That's their job. You'll also notice, if you look very carefully again, that these peaks are not exactly the same height. And that's because this center tap on the transformer is not exactly at the center. I'm going to exaggerate that. So they might look like this. They don't look anywhere near that drastically different, but there's a difference between the height in the positive part and the height in the flipped over negative part. This is going to be a very small fraction of a volt because it's really very, very closely connected to the center tap. Now that's going to become important in the last part of the experiment. So let me erase this, because this is what you'll see. Measure this carefully. Is that 22.5 volts or whatever you got before? Is it less? Is it more? It should be the same because you're only one diode or the other, and all diodes of the same type have the same junction potential roughly. You're going to get pretty much the same voltage one way or the other, provided the center tap's exactly in the center, which it isn't. So erase this. And so we have an output, a full wave output like this. Sine waves, not quite the same height every other one, but this is versus time, and this is, of course, voltage. That's what you always see on an oscilloscope, voltage versus time, really, almost always. We know that we can make Lissajous patterns where we see voltage and voltage together, but normally that's the way they're used. Okay, so here's this 1, 2, 1, 2, the alternating current running through, alternating current flow running through this resistor from diode 1, diode 2, 1, 2, 1, 2, and so forth. If you, and we already know this, one cycle takes 1/60th of a second because it's 60 hertz. Thanks to the power company, it's almost exactly 60 hertz. And we checked that out when we did the oscilloscope lab. We're doing both of these labs, as you know, so that everybody does the oscilloscope lab and then everybody does the diode lab, so that you have that background with operating the oscilloscope here and know how it works and what it's showing. If this is not exactly in the center tap, these peaks are going to be a little bit different in height. That's one problem. Now the other thing is this cycle is a 60th of a second, so each one of these peaks takes 120th of a second. That's how long this is in time. Here's the last part of the experiment that we're going to do. We're going to just leave that whole circuit wired up, and we're going to put in one of our capacitors, which we studied a while back, in parallel with the resistor. So this is the last part of the lab. So, and again, don't forget it's an electrolytic capacitor, so you want to hook the positive side up away from the ground, and the bar on the capacitor goes towards the ground. So here's your capacitor, and here's the bar down here that would go towards the ground. So what does that do? Well, this turns this into an RC circuit, which we studied back when we talked about capacitors, which is kind of interesting. RC circuits have a time constant, and the time constant is RC. That is, resistance in ohms times capacitance in farads is seconds. Remember, we had V equals V0 e to the minus t over RC. That being a time constant because that exponent here has to be unitless. And so RC, believe it or not, 1 ohm times 1 farad is 1 second. Okay, so you have a 100 microfarad capacitor, which is 1 times 10 to the minus 4 farads, and 10,000 ohm resistor, which is 1 times 10 to the plus 4, right? So when you multiply C times R, you get 1. So the time constant of this little circuit, this little RC circuit that you've made here, is 1 second. Now, wait, this is 1/120th of a second. So there's going to be 120 of these pulses before one time constant goes by. What that means is, now that you've done this, the capacitor only has a little bit of time. Remember that your time constant. Here's the capacitor discharge, and the time constant was when you reach, if this is V0, this is V0 over E, which is roughly 3. So you reach 1/3 roughly of your original voltage. That's the time constant time. And you measured that in many cases in that lab. So this means that if you wait for 1 second, if you could wait for 1 second, this capacitor, if it's charged up to this voltage, would take 120 of these pulses to discharge down to 1/3 of its voltage. But it doesn't get the time to do that, because in the next 120th of a second, there's another pulse, charging that capacitor back up to pretty much the same voltage. So what happens is that capacitor doesn't get much time to charge or discharge. If this is 1 second, 120th of a second is just barely past 0 here, and that means the voltage only goes down a little bit. Okay, so let me trace out the voltage that you will see on the oscilloscope 2, and it's going to look like this. Take away all this, which you can do with your AC-DC switch. You can only look at the AC. You're going to see this sort of thing, where you just see the tops of each one of these peaks, and you let the capacitor discharge just a very little bit until the next peak charges it back up. So this is called ripple. And you want to measure and also calculate, using the formula that you're given, the ripple factor, which is the AC voltage. In other words, the ripple, this looks like a little AC voltage, divided by the DC voltage, which is this voltage here, which is around 20 volts, as you already measured, right? This little ripple, let's say this little ripple is 0.2 volts, peak to peak. You have to turn your oscilloscope gain way up to expand it on the AC scale, filtering out this 22 volts to look at it, and you'll see it's maybe, let's say it's 0.2 volts. So the ripple factor is 0.2 divided by 20, which is 0.01. So the ripple factor then is 0.01. You can calculate the actual ripple factor and the theoretical ripple factor by the formula, the actual ripple factor by doing what I just suggested here, which is pretty easy. All you have to do is flip your AC-DC switch on channel 2 from AC to DC. When you switch it to AC, it gets rid of your 22 volts and only lets you look at in an expanded way the ripple. So check out your ripple, and you'll find that your ripple factor is going to be probably a lot higher than you theoretically think it should be according to the calculations from the theory, because these two peaks are not quite the same height. So what's going to happen, and I'm going to exaggerate this, when your voltage charges up to peak 1, it's going to drop off, and if this other peak is lower, it's going to drop off much farther than it would. Then if this next peak is higher again, it's going to cause the ripple factor to look larger. It could look 2 or 3 times larger, depending on how closely your center tap is exactly at the center. So those are the numbers you want to get, and you want to get them as accurately as possible by measuring your oscilloscope vertical distance, the voltage distance to the nearest millimeter, and talk about your results. That's it.